All right. In the practice quiz, we had a problem about clustering, and a lot of you were getting a little worried about how to work it out. So don't worry about it. It was just for you to sort of get familiar with gradients more than that clustering algorithm. We will cover that in the last month. So and then you'll probably understand it more. But if you got it, fine. If not, don't worry about it. Okay. All right. So let's get started. In last class, we were looking at version spaces, right? So version space is essentially a set of all hypotheses that are consistent with your training data set. Okay. So we looked at a few terms. We looked at something called consistency. We looked at something called consistency, right? So consistency is a property of a hypothesis, right? And with respect to a training data set, right? So a hypothesis is consistent with a training data set if it correctly classifies all of the examples in that training data set, right? So whatever is malignant, it should call them malignant. Whatever is benign, it should call them benign, right? Very easy. So at any given point, when you have some training data set, you would have some hypotheses which are consistent with your training data set and some which are not. So think about it this way. So remember, let's say this is your hypothesis class, right? So for example, conjunctive concepts. So let's say these are all conjunctive concepts. And right now I have some training data D. Okay, let's say these are some 4 or 5 points. This one is malignant, malignant, benign, benign. It could be anything, and these are the features, right? So some of the hypotheses, so think of this class as a bag of hypotheses, right? So some of the hypotheses here would classify all of them as correct. Some of them might make a mistake on at least one or more of them. So the ones that classify them correct, right? This is what we call the version space. All right. So the version space will contain every hypothesis that is consistent with your training data. So what you see is that as you add more and more training examples, your version space can only shrink. Okay, it can stay the same or it can shrink, because when it can never grow bigger. Why? Because if you get a new example here, and let's say that's malignant, you cannot get, suddenly there cannot be a hypothesis which was not in the version space before which can now come to the version space, right? That's easy to understand, because that would mean that in the past that hypothesis was not agreeing with at least one of these examples. That's why it was not in the version space, which means that if you include it now in the version space, it will not agree with one of these, and that's a contradiction. It would not be in the version space, right? So that's kind of the idea, right? So we looked at one algorithm called list then eliminate, which tried to learn this version space. So we are now moving away from the job of finding the right concept, because we saw in the case of find S that it's hard to get to the right concept if we do not have enough training data, right? So we have loosened the requirements a little bit and said that how about just trying to learn the version space, because the target concept is guaranteed to be in the version space, right? So we saw list eliminate, which was one very sort of a naive way of finding this version space, which essentially starts with the entire version space, and every time you see a new training data set, it goes through every hypothesis and tosses out anything that does not agree with that new one, right? However, as we saw, that it's not a very efficient algorithm, because every time it has to go through the entire it has to go through the hypothesis, the version space, which starts as 3 power d plus 1 if these are conjunctive concepts. So every time it has to do a lot of computation. So today we are going to look at a more efficient algorithm. So let's just call list eliminate not efficient. All right. So to understand this new algorithm, we've introduced this concept of boundaries of a version space. Okay. So boundary. So what we saw in the last class was that if you look at version space, which essentially is a set of hypotheses, right? you can arrange them in an order. So there is an order that we defined which was called more general than order, and then you can have an ordering of a partial ordering of all of these of all of these hypotheses in the version space. Okay, so at the bottom would be the most specific hypothesis, and at the top would be, well, at the bottom will be the most specific hypotheses. There could be multiple, and on the top there will be most general. Right? The idea of most general and most specific is that you cannot have anything more specific than the most specific one. If you have something more specific, then it would start misclassifying some of the examples in your training data set, which means it would not be in the version space anymore. Right? Same thing with most general, is that if you go any general than that, you will start misclassifying, so it won't be in the version space. Right? So it's very easy. Of course, in the case of now comes the question, like, what is more general than something and more specific than something, right? So we had a exact definition of that, that's there in the slides. All right, that was right here. So we had a mathematical definition of that. Essentially, something is more, one hypothesis is more general than another if it classifies, it covers all the examples that the more specific one does, and then some more, right? So that's the idea. In the case of conjunctive concepts, it's easier to define. It's relatively easier. But the point I'm trying to make here is that this ordering, this relationship of more general and more specific, is not restricted to conjunctive concepts. It's for any concept, right? But the way we define it for for the conjunctive concepts is that we are looking at more general than relationship. Is that, let's say you have a hypothesis like this: small dark irregular question mark question mark question mark. Let's say this is a hypothesis, right? So a more general than hypothesis would be something which has a fewer specifications. So this is more general than. Now what you can see is when you compare this to the definition we have on the slide, it agrees with that, which means that if this hypothesis calls something positive, this hypothesis will also call that positive. But there are some examples which this will call positive and not this one. All right, so that's the idea. And then you also have a definition, similar definition for more specific. So for example, let's say it's symmetric, right? So this hypothesis is more specific than this one, right? Because it has more specifications. It's more restrictive. You can think of it that way, right? So if you remember our space of conjunctive hypotheses, the most specific hypothesis would be this, the one that does not accept anything as malignant, right? Which rejects everything, reject all or accept nothing. Why? Because it does not cover anything. So the number of examples it calls positive is 0, right? And the most general would be this one, which calls everything malignant. So because it covers everything, and then everything else would be in the middle, right? So this is the sort of a version space when you have not seen anything. But of course, so now what this lets us do is define these boundaries, which means that there are some hypotheses that for a given training data set, there would be some hypotheses which would be on the top, which means you cannot go any more specific, and some hypotheses that are in the bottom. So that's called the specific boundary. A most specific boundary and most general boundary. So as you see more and more data, what will happen is that these boundaries will move, right? If you get enough data, if you are lucky, it would so happen that you would be left with only one hypothesis in your version space, which will be a target concept. But even if you do not have enough data, you would have a version space which is guaranteed to contain your target concept, right? So that's the idea. So now we will look at one theorem which kind of allows us to apply one algorithm, all right? Oh, why does it do that all the time? All right, just to further expound on that point. So if you look at this example, we have been looking at this example from last week, right? So this is your training data set, and on the right are some of the hypotheses that are consistent. So that's the version space. So what you will see is that you can arrange them in this way. There will be other, well, this is not your entire version space actually. These are just a few hypotheses which are consistent, but there could be more. But what happens is that the top one is your most specific hypothesis in this version space, and the bottom two are the most general. So the reason I call it a partial ordering is because you do not have an ordering between these two, but in general you can arrange it like this. So you cannot go more general than this. If you go more general than this, then you will start making mistakes, and if you go more specific than that, you will start making mistakes. So there is a theorem which we will not go into too much detail, but it's very easy to understand. The idea is that if you have any hypothesis in the version space, it is guaranteed to be contained within this boundary, right? Because there cannot be any hypothesis which is part of the version space but outside this, right? To be more specific, what this says is that if you have any hypothesis that belongs to the version space, then you can find two hypotheses, one in the general boundary and one in the specific boundary, such that this hypothesis will be more general than one and more specific than other, right? So the idea is this. So what this theorem says is that what is called version space, right? Version space representation theorem says is that if you have your specific boundary, right? And how do I write it? Yeah, specific on the top, and this is your general boundary, okay? So remember, general boundary and specific boundary can contain more than one hypothesis, right? So this is a set, right? So if I take any H that belongs to the version space, then I am guaranteed that there exists a pair of hypotheses, one from here, S belonging to this big S and G belonging to this big G, such that this ordering exists, that H will be more general than the S and S will be more general than H. All right, so that's the theorem. On the slides I have written it in another way, but it means the same thing, right? So H is more specific than G and H is more general than S, right? So that's the guarantee that this algorithm provides you. So with this theorem, right, with this proof, and in the handouts I have a proof, but the reason I don't go into the proof is it's kind of not very mathematical, it's just sort of argument, so you can easily follow it. I mean, the way to follow it is you can do it in two steps. One is you prove the right hand side and the left hand side. So first you can say that, hey, let's assume that there is a hypothesis that belongs to the version space. Now you show that yes, there will be two hypotheses, G and S, which will contain it, and that's easy to show through contradiction, and then the other way around, right? However, the interesting part of this algorithm, this theorem, is that what that allows us to do is that it lets us come up with a new algorithm. Okay, it's called candidate elimination algorithm. And what candidate elimination algorithm does is that it only tries to learn the boundaries, because once it has learned the correct boundary of your version space, then by that theorem all the other hypotheses in the version space will be there, right? So that way it's more efficient and it works faster than list than eliminate. That's the basic idea. Okay, so the idea behind candidate elimination is, we'll first look at it in a more sort of a intuitive fashion, then I'll go through the steps, which I would recommend that you go through them after the class as well. You'll need that for the gradients quiz anyway. And then we'll also look at an example. Okay. So the idea is this: you start with your boundaries as the most specific and most general, as we have seen before. So when you haven't seen any data, right? Oh, I forgot to ask, did you turn on the mic? Oh, the camera. Thank you. Okay, so candidate elimination. So what we do is that first we assume that we have not seen anything. So that means that your most general hypothesis or your general boundary is essentially all question marks, and your specific boundary is the most specific hypothesis, right? So this is your S, this is your G, and then as you get your training data one by one, you keep modifying them. Okay, you keep bringing them up or down and sort of converging towards the actual version space at every step, right? So the way it happens is that you remember in the find us algorithm, you only consider the positive examples or the malignant examples, right? In this one, you do something for malignant and do something for specific, right? In particular, what happens is that if you get a malignant example, you will fix your most specific boundary. You will bring it down because now you have seen something malignant, right? So you try to adjust the entries that would make that positive example incorrectly labeled, and you bring it down. And when you see a negative example, you bring this up. All right. So I'll quickly show you the steps. I will not go through the steps like step by step because kind of takes a lot of time, and it's easy to understand. So when you see a positive, so you have initialized your training data. Now you get a training example, right? So first, let's say you see a positive example, a malignant tumor or something that belongs to the concept. So the first thing you want to do is you want to ensure that whatever is in your version space right now is consistent, right? So the first thing you do is you remove any hypothesis in the most general boundary which violates or which does not agree with this concept, because if you don't do that, then it will not belong to the version space anymore, right? So you do that, but the real game here is that you look at your most specific boundary, right? And then you toss it out. You toss the most specific boundary from that, whichever does not agree with your training example, and then you generalize it. So you toss it out, but before tossing out, you generalize it. So generalization means that if you have a hypothesis, you can generalize it by replacing some of the actual values by a question mark, right? That makes it more general. And we have to do minimal generalization, which means you can only remove one at a time, not all, not two, not three. So that way you are moving it one step by step, right? And what you do is you consider all possible generalizations of every hypothesis in the most specific boundary which does not agree with your training data point, and you add it to your this specific boundary if two things happen. If it agrees with your training data point, which it has to, otherwise it won't be in the version space, and if you have a corresponding general hypothesis. If you have a hypothesis in your general boundary which sort of covers that, right? Because only then you will be ensuring that this is in the boundary, okay? So if those two things happen, then you add it, otherwise you don't, and you keep doing that. If you see a negative example, you do the reverse, right? In a negative example, of course, you first check if your specific boundary is sort of okay with your new training data point, and then you take every G, okay, every every hypothesis in your general boundary which does not agree with your training data point. The ones that agree will stay there, right, because they are part of the version space even now. But if it does not agree, then you remove it. But before removing it, you consider every minimal specialization of G. Okay, so specialization is the reverse. So for example, if you have something with a question mark, you can replace it with one of the values. Okay, and then you again see if there is a corresponding thing in your most general boundary, and then if it does, then you add it to your most specific or most general boundary, and you keep doing that. All right. So it's the steps, you have to be careful with the steps, but in general the idea is very simple, right? You're trying to sort of go narrower and narrower. All right. One thing I want to point out, because you will see that issue coming up in your gradients quiz, is this. So there's some notion of what I call minimal generalization. So minimal generalization means that if you have, example, if you have a hypothesis which is like this, small, dark, irregular, question mark, thin, question mark, then a generalization of this, the minimal generalization would be question mark, dark, irregular, question mark, thin, question mark, right? That would be one possibility, but you could have many, right? You could have generalize this one, or you could have generalized this one or this one. These you cannot generalize anymore, right? So that's the idea. The same thing with minimal specialization is that, let's say you had this one again, small, dark, irregular, question mark, thin, question mark, then a specialization could be, you cannot specialize these ones anymore because these are as specialized as you can go, but you certainly can specialize the question mark. So you can replace this with whatever this was, something. What are the other attributes? Smooth, but that's irregular. Circular, right? Sorry. Yeah, so like you can make it circular, and thin and question mark. Okay, and so and you can also specialize this one instead of this one, but it has to be only one at a time because that's minimal generalization, minimal specialization. However, one thing that you need to be careful about when you're doing minimal specialization is that, let's say your attribute takes more than 2 values, let's say it takes 3 values, right? Then let's say this one was the shape, and let's say it was circular, oval, and square. Okay, these are tumors. Well, anyway, square. So then you have to consider this with circular, this with oval, and this with square. So all 3 will be the part of the minimal specialization. Okay, so you have to be careful with that. So when you do your gradients quiz on candidate elimination, there's that twist in that problem where one of the attribute takes 3 values. So you have to be careful when you're doing that. Any questions so far? Yes. So remember, when you're doing your when you're running through this algorithm on certain data set, what will happen is that you have to, in the step 2 in each side, you have to do this minimal generalization or minimal specialization, right? Minimal generalization is easy to do, as I showed in the sheet in that example, that if you want to generalize any hypothesis, all you do is you replace one of the entries which are there, right? Sometimes we also call them literals. So one of the literals which is present, which is not a question mark, you can replace it with a question mark and only do one at a time, because that's the minimal part. But if you have to do specialization, you have to be a little more careful. So if you have something like this, to specialize this, you have to consider, if you replace it with the actual values, then you have to consider all possibilities, however many it takes. So if it's binary, it will result in 2 minimal specializations. If it takes 3 values, then there will be 3, and so on, right? So that's sort of one note of caution when you're running this through a given data set. Right. Oh, that's the true label, right? So because this is the training data set, it means that you're looking at a training example, you know its features, which is X, and then you also know what its true label is. Is it malignant or not? And using that label, you are basically trying to update. It's malignant, right? It's benign, right? Exactly. And you know, I'll probably abuse this notation a lot of times. Sometimes we'll call it +1, -1, or 1 or 0. But in general, if it's 1 or true or positive, it's the belonging to the concept and otherwise not, right? So this is kind of like a classic machine learning algorithm. You have some training data, you start with some hypothesis about your model, and you refine your model as more and more data comes. You have a question there?
Does it matter, going back a little bit,
yeah.
Does it matter what you sign malignant and what you sign benign, or can you reverse them? If you're saying malignant is a positive, benign is a negative, can you?
Right, that's a good question. So question is that does it matter what we call positive and what we call negative? See, so here what we are doing is a concept learning, right? So at the get-go, you want to identify what is your concept, like what are you trying to differentiate from everything else? So are you trying to learn about malignant tumors and everything else, right, which would be benign in this case, or the other way around? You can do it other way around, but then you have to be careful when you're doing the predictions. When you get a +1 or a true, then you should know that this is a benign tumor, because that's what you started off learning. But yeah, that's a good point. See, in some case, I mean, the easy answer is that it does not matter, but you need to be careful. When you're using it, then the output that you're getting, you need to use it in the way that you started off with, right? All right. Okay, any questions about this? Cool. Yes, go ahead.
If you're doing the minimal generalization, and there's a certain attribute that has 3 values it can be, are you still changing it to a question mark, or would you just change it to
All right.
circular, and then you got one that was an oval, would you just change that attribute to circle or oval, or would you change it to a question mark?
Are you talking about generalizations, right?
Yeah.
So in a generalization, the easy part is that the thing that you're trying to generalize will only have one value. It would be either oval or circular or square, right? So you would change it into question mark. That's the only one that you would change, unless you had another see here, right? Let's say let's consider this. Let's say we are trying to generalize this, right? Now this one we know it actually takes 3 values, right? But in this hypothesis, that's the only value it is taking, right? So when you're trying to generalize that, this would go convert into question mark, nothing else. You will not have to consider the other possibilities. You will consider them when they come in your processing, right? When you're generalizing this hypothesis, this is the only hypothesis that you have to consider, right? So this one will only give you, at least when you're trying to generalize this attribute, there will be only one possible generalization, which is replacing it with a question mark, right? Okay, so let's move on. So you might think that I sped a little bit on this algorithm, but it's a fairly easy algorithm. It just has steps that you need to follow. Okay, so once you do your quiz, you should be able to follow it in a much better way, right? I do want to point out some. So we can go through this example, or you can go through. I'll go through it very quickly. So let's say this one we are trying to run the original data set that we had earlier, right? So we start with this, right? Your most specific one is this, most general is this one. Now you get a positive example, right? So when you get a positive example, the first thing you check is, does it violate any of these hypotheses? So it does not, right? This one will call anything positive, so this is fine. Then you look at this one and you try to generalize it. You try to generalize it, right? So the first generalization that you get, of course, is the most specific generalization. The minimal generalization of this would be this, because this is the one that agrees with this one, right? And you will keep it. Then you get another positive example. Then you will generalize this one. right? And you will consider all possible generalizations, but what you will see is that only this one sort of agrees with this, so it will be part of this. And at every step you also have to see that if I want to choose this into my version space, there needs to be a corresponding one in my most general space which sort of covers it. But in this case it will, because this is the most general thing, this will cover everything, right? Then you get a negative one things sort of explode, because now you have to consider all possible specializations of this. So all possible specializations, of course, you know, you will consider all of them, but only a few of them will be consistent with this data set, and only a few of them will have something here that sort of is the more specific version of this. So the reason these are crossed out is that these ones are either not, you know, part of this, or these ones do not have something, a partner here, right? And then so on. So you get another one and so on. So at some point you stop, right? So let's say you have this is your training data, you will stop at this point. This is your version space. Well, this is not your version space. These are the boundaries of your version space. You cannot go any more general or specific. You could have more hypotheses inside, but you're guaranteed by that theorem that these will be your target hypothesis is contained in these boundaries. All right. All right. So now let's sort of look at this algorithm a little more. So the question, of course, the easy way to understand is that at every step you are trying to converge the boundaries towards the target, but the important question is, will it converge, right? And that is a question that you will see in every machine learning algorithm. Whenever you design an algorithm, the first question people will ask is, will it converge to the right answer, right? That's easy. I mean, that's the most obvious question. So the answer to that is that it might not. It will converge if you have enough training data, right? And also if you do not have any errors in your training examples. Now, one thing about this is that if there is any error in your training data, because what will happen is that it would just become empty very soon, in the sense that there will be nothing in your version space because you have an error, okay? And think about it a little more. I have those explanations in the note. And also the last thing, which is that the target concept needs to be in that hypothesis space. If it is not, then you are essentially you know, starting off at a wrong with the wrong step, wrong first step, right? But if they are not, if all of these hold, then it will converge, okay? Now, of course, we have seen why it is better than find S. It is better because it's more efficient. Another thing is that the good thing about this algorithm is that if there is a mistake in the training data, at the next step, your version space will become empty. And you can, if you think about it a little more, you will know why. Otherwise, you can refer to the notes. Now, since your version space becomes empty, you will know that there was a mistake in the training data, okay? So it is not robust to the mistakes, but it will at least tell you that there were issues in the training data, okay? Which means that, you know, then you can use it in a little more informed manner. So that's another way it is better than find S. Now, what happens if you do not have sufficient training examples? Which means that what happens if it has not converged to the right target concept, right? So ideally what you would like to have is that when you have seen all of your training data, there is only one concept in these boundaries, which means that which means that this is the most specific and this is the most general, just for example, right? But if you do not have that training data, you would have a whole set. So how do you use that, right, to make your predictions? So one way to do it is that you can use the boundary sets to test against your test example. So let's say you get a new test case X star. You do not know what its true label is. You want to use the model that you have learned from candidate elimination to make the prediction. So what you do is you try it with every hypothesis in your both sides, S and G, and then many things can happen. One thing that can happen is that X star is consistent with every hypothesis in S, which is a very good case, which means that you will call it a malignant instance because everything that is most specific is agreeing with it. Other is that X star is inconsistent. Inconsistent means that it does not agree with anything in G, then you call it benign because it is not agreeing with anything in G. The reason being that if it is inconsistent with anything in G, then you are guaranteed that it will not be consistent with anything above it, right? Because the most general one is rejecting it, so anything more specific than that will reject it. And the other way is also the same thing, that if it is consistent with everything on the S, right, then anything that is more general than S will accept it as well, right? So those are clear cases, but there could be another case where, now I have some examples here. So let's say this is your this is your most specific boundary, this is most general boundary, and these are all other hypotheses that are in the version space. And because of the theorem, you know that each one of them will have something here which connects them, right? So let's say this is your new training example. What will happen is, if you look at this one will be accepted by everything in the most specific boundary, right? In this case, there's only one thing in the most specific boundary, and that will accept it because it agrees LA, LA, LI, LI, TH, TH, right? Which means that you should call it malignant because everything else will also agree with it. Same way with this one will get rejected by both of these in the most general hypothesis space, most general boundary, which means that nothing else will accept it as a malignant tumor, which means you should call it a benign tumor, right? See, the reason I'm saying that is because if nothing else accepts it, it means that the target concept will not accept it either, right? Because the target concept is going to be somewhere here, right? So that's easy. But what happens if you get an instance like this one? If you look at this one will not get accepted by this one, right? Of course, but it will get accepted by these two, right? Which means that now you are in there's a confusion there, there's an ambiguity there, that some of the hypotheses in that version space are accepting it, some of them are not. So now what do we do? And that's where we have to come up with our own choices. For example, you could say if more than half of the hypotheses are accepting it, I will call it malignant. If less than half, then I'll call it benign, right? You can come up with something else, which is, you can say I'll just pick some at random, and if they are with a majority, if they are classifying it as malignant, then I'll call it malignant. So these are some of the choices that you have to come up with. So there are certain algorithms that I kind of mentioned just now. So halving algorithm is one of them, right? Halving algorithm, what it does is that if at least half of the hypotheses in the version space are calling it malignant, then it will call them malignant, otherwise not. There's a randomized halving that sort of only uses a random selection, and all of them sort of work well in practice, and there are some theoretical proofs on how well they will do, okay? But that's sort of beyond the scope of our course right now. Any questions about that? All right. Okay, so now let's look at the last concept in part A, and then we can move on to part B. No, last concept in part A2. All right, the notion of inductive bias. Okay, so and we have talked about it actually in the second class, but remember that we talked about this earlier, that if you have a training data set X, then all possible hypotheses that there can be are actually 2 power d, right? 2 power size of X. It's a very large space, but because that's a very hard task to search the right concept in that, what we do is we say that our hypothesis is actually in a smaller space. In this case, we said it's in a conjunctive space. So that notion is called the inductive bias that we are applying to our search. Okay, so for example, in this case, we made an assumption that your target concept is conjunctive, which means that we narrowed our our hypothesis space. So that's called the inductive bias. We are from the get-go, we are biasing our search to only look in this area, right? So in future, whenever you are looking at any machine learning algorithm, you need to think about it. The first thing you want to ask is, what is its inductive bias, right? We will see things like linear regression, logistic regression, neural networks. Each one of them works with some inductive bias. For example, linear regression, For those of you who have not looked at it yet, don't worry about it. But the idea is you're trying to learn lines, right? So there, you are putting an inductive bias that my answer is in all possible lines. One of the lines is my answer. So that's my inductive bias. In the case of candidate elimination or find S, we are putting an inductive bias that my answer is only conjunctive concepts, right? So that's the bias that we are providing, and that's sort of pictorially, I drew this picture earlier, that my answer is here, but my all possible concepts are a much bigger space, right? But we put a bias, which is this red circle, and then look for the answer over there, right? But if your answer is, if your right answer is not in this, then you would not be able to learn it with that algorithm, which, because the bias that it applied does not cover the right answer, right? So that's the idea. Now somebody could ask, is there something called bias free learning? Can we learn without putting this bias, right? Because we know that this is the target. What if we just say that my right answer is somewhere here? I do not make any bias, which means that my red circle is as big as this big circle. Can I find the right answer, right? So that's called bias free learning. It turns out that you can learn from that setting, but the amount of data that you will need to learn will be the same as the size of X. Okay, so I have a small example in the handout which kind of elaborates on this point. So the point I'm trying to make is that if you do not put any bias on your hypothesis space, then you will need as much data as there is in the whole world. In the sense, you know, if your world is made up of d binary attributes, right? So you can have 2 power d examples. You will need 2 power d examples and their labels to learn without any bias, which means that it's useless, right? Which means that you need to know everything about everything to make future predictions, but you already knew, you know, the right labels for them. So that means that bias free learning is useless, it's futile, right? So think about this. So let's say you have to give an exam tomorrow about multiplicative tables, right? And you would be asked questions like, what is 6 times 4, what is 6 times 5? So one thing you could do is you can sort of not apply any rule and just learn every possibility. Learn what is 6 times 1, what is 6 times 2, what is 6 times 3. So now you have learned, but because you have learned from a data which had all possibilities, now when you go to the exam, they will ask you what is 6 times 6. You will know it, but the reason you knew it is because you saw 6 times 6 here. So without any bias, you need to know the exact example here to make a prediction here, okay? Which is essentially the notion of bias-free learning, which essentially means that it is useless. So as I said in the second class, in machine learning, you need to have a bias to do some reliable learning, okay? To do some efficient learning. Any questions about that? That is more of a philosophical argument. So, so we have seen a few algorithms, right? We have seen find S, we have seen candidate elimination, and then the example that I was trying to convey was this, what we call rote learning. Okay, rote learning means that you can make a prediction on what you have seen exactly in the past and nothing else, because you have no bias in your mind, right? So, so we were looking at this example of trying to classify students into undergrad versus graduate, right? So let's say in my training data, I had one person and I knew he's an undergrad. If I have no bias, then tomorrow if I see the same person, I can say that yes, that's an undergrad. But if I see a different person, I will not call him grad or undergrad because I do not have any bias, right? Which means that I cannot do any learning. So that's called rote learning. So rote learning has no bias. Candidate elimination has a little more bias. You are still putting a bias that your data is in this space, your hypothesis in this space, but you are still trying to learn a version space, not the exact answer. And find S has the strongest bias because you're trying to say, because what you have said is that your answer is a conjunctive hypothesis and nothing else, all right? So that's the idea. So what you want to, now when you're designing new algorithms, right, you need to be less biased right? Because essentially if you have a lesser bias, it means that the radius of this circle will be larger, which means that the chance of the right answer to be in that circle would be higher, right? But if you make fewer bias, smaller bias, then you will need more data to train, right? So the magic is in trying to find the right level of bias, right? If you go too big, you will need more data. If you go too small, then the chances that the right answer is not in that circle will be higher, right? So there's a trade-off there. So that's the point of this. All right. So there are some interesting papers that talk about what we have seen today. So you can look at that as well. All right. Any questions so far? I have 5 minutes. So I'm going to start this new topic and then we'll come to it on Wednesday. How much more time? 3 more minutes. Okay. So when I come back on Monday, I'm going to talk about this thing called online learning. Okay. So this is a new setup of learning. So there are two types of machine learning setups. So one is called batch learning and one is online learning. Batch learning is where I give you a set of training data and you do something with it and you come up with a model. That's your machine learning model, and then whenever you get a new example, you can make a prediction, right? The other one is online learning, in which you keep refining your answer as you get training data, right? And at any point I can use it to make predictions, right? So that's an online setting. So it's a pretty easy sort of setting here. So online learning with mistakes is that you have some training data which is binary. So now I've changed it again. Now what I'm saying is that you have D attribute. This is sort of a set notation, right? So your X is defined over D attributes. Each attribute is binary. In this case, I'm calling it true or false. It could be 1, 0 or whatever, right? Then you have some training data in which you have a subset of these examples as well as the label. The label is given to you by a C, a function that takes a training example and spits out 0 or 1 or true or false, positive, negative. Okay. So this is how online learning algorithm works, right? The learner or your learning algorithm gets an example X. Then it makes a prediction on X based on whatever it knows. That's C star of X, I. And then you tell what the actual X was, what the actual C of X was, right? And then it does some updating of its own, because now it has seen some answer, and then it goes back. So that's the online learning, which means that at any point it is making a prediction and then it is also updating itself, right? Compared to a batch learning where it will need all the training data and it will do its magic and then only then it will be ready. So online learning is a little different. Now the task for us is to learn the C, right, with minimum number of prediction mistakes. That means that, so the two things can happen here, right? Once you get an X, you will predict what you think is the right answer, and then you are told what the right answer is. Now these could be the same, which means you have not made a mistake, or these could be different, which means you have made a mistake, right? The objective is to learn the C with minimum number of prediction mistakes, right? Ideally 0 mistakes, but that's not possible. But you want to be able to come up with algorithms which can make minimum number of prediction mistakes. So from next class onwards, we'll try to we'll try to analyze algorithms based on this criterion, like how quickly can it learn the right answer, and by quickly I mean minimum number of prediction mistakes. Okay, any questions so far? Fantastic. All right, I'll see you on Wednesday. Thank you very much.